the idea here is we want to take this, this new feature that exists within hardware and move that into a true infrastructure as a service development environment. OpenStack provides the perfect setup for this. It's free and open source. There's an extremely large development community. It's very easy to use, as I'm sure most people know here through previous days' examples of using Eucalyptus, specifically on FutureGrid. It just works in many cases, which is not always true for some other cloud infrastructure as a service technologies. So OpenStack really is a big up-and-comer recently and has a lot of promise to it. And it's open source, it's all Python, it's very easy to modify when it comes down to it. So this solution actually is using the Zen API provided by XCP with a modified 412 hypervisor to actually provide not only PCI pass-through to a given Zen VM, but also make this aware and possible within OpenStack. So specifically, I won't go into the entire architectural detail of OpenStack. It's actually very large and complicated. But just to zoom in a little bit, we take a look at the Nova compute and the connection, the driver connection to the underlying hypervisor. This is where we're actually modifying, this is what we're working with right here. Specifically, we run the OpenStack compute instance within a paravirtualized DOM-U that will connect directly to the Zen API that exists with DOM0. This is advantageous for a few reasons. First, you have natural isolation of your OpenStack compute instances, and you can shrink or grow the resources necessary to run your Nova compute depending on your load. Furthermore, it provides a nice security isolation standpoint, which for public clouds matters. So even if somehow Nova compute daemon gets hacked, you don't automatically lose access and give up root, like a root shell to domain 0 where potentially harmful things could take place. But from here, it allows you to create a tenant VM through OpenStack that allows users to run your NVIDIA CUDA code directly, or OpenCL code for that matter, and directly communicate and utilize the NVIDIA Tesla GPUs or any other GPUs. This implementation, while we concentrate on NVIDIA GPUs, is actually, for the most part, agnostic to what accelerator card you use. So it's very easy to swap this out and use an AMD, for instance, which is unlike most other front-end remote API mechanisms, which are specifically built for the CUDA environment. So not only do we have a potentially higher performance and a less complicated solution, we also have more flexibility as well. And we treat this no different than any other infrastructure as a service instance. So this is a current, ISI OpenStack user interface, our dashboard. If anybody's ever used the OpenStack dashboard, this should look very familiar. But the idea here is that all you have to do is pick a CG1 instance, basically a flavor specifically targeted for GPUs, and this will give you 1, 2, or 4 GPUs depending on what flavor you pick. And then you can have your instances specifically set up for this environment and run it just as you would in Amazon EC2 or any other OpenStack or Eucalyptus environment. This also is not specific to the dashboard. While it's easiest to show in the dashboard, you can use the Yuka run instances commands just as you would, again, with any other infrastructure service. So the idea here is we're building these GPUs directly into the infrastructure as a service architecture, which has a number of advantages. If nothing else, most of you guys today are already familiar with how to use this technology. There's no learning curve other than actually learning how to program in CUDA, which is again a separate issue. Good news on performance thus far. Again, this is an early technology preview, but so far we're seeing efficiency numbers anywhere between 89 to 99% of native performance. So Monte Carlo simulations where we have a lot of back and forth between the CPU and GPU, we notice the biggest overhead at about 89 to 90%. This is just using the CUDA benchmarks thus far. For running CUDA BLAS or CUDA matrix multiplication, this overhead decreases to almost nothing. where we're seeing 99.4% the performance as you would get as if you were running this on a native host operating system. For FFTs, it varies depending on your 1, 2, and 3 are different parameters, of course. So it varies depending on your workload, but either way, this is good news. And comparing it to what we can see from like an apples to oranges comparison, because we don't have equal hardware, of looking at implementations using our CUDA or gVertis, this is actually showing a lot of promise thus far. So this is good. This is good news for us. This gets us really excited and shows us our efforts are not in vain. So where do you go from here is a really interesting question. Without a doubt, GPUs are here to stay within scientific computing. They have been used extensively for the past couple of years, and their implementation continues to rise. Every year, the top 5, for the past 3 years, the number of GPUs on the top 500 list has doubled. This is a very substantial doubling, and now I think more than 1/10 of the supercomputers listed on the top 500 directly use GPUs. So that's a very striking difference from 3-4 years ago, for instance. And this will, as many people are expecting, continue to grow as we look towards exascale machines, which are specifically set up using various GPU systems. Whether or not we'll get there and when and what it will actually look like has, of course, yet to be determined, but GPUs are certainly a major function on the roadmap. As you know, I'm sure you guys have heard many times before, and definitely by Dan's last presentation, we want to actually use, many scientists want to use high-performance computing tools just in the exact same way that clouds exist today. So being able to provide these resources, these classic, if you will, classic HPC resources within a cloud has a number of advantages. And one of the first steps into making that happen is to provide these GPUs directly within a cloud infrastructure as a service. And from there, OpenStack fits the bill quite nicely for us, and yeah, currently working on that. We have some development systems up and running here at ISI. They're out and at various container sites. They're not public, but my hope is to have this in a infrastructure set up relatively soon, perhaps using FutureGrid.